Okay, so now the problem of live on YouTube has been resolved. So, okay, what I was telling you that uh, whenever we are depositing parts, what is happening is that there are residual stresses are being developed. Residual stresses are like the stresses which remain in the body because of the pre-component which is not being released, because you know that 3D printing or additive manufacturing is layer by layer. So whenever one layer gets deposited on the top of the other layer, it leads to generation of some stress. And primarily it happens because of the thermal effects. And this is one thing which is a major limitation of additive manufacturing process, because this is the major factor which influences the part geometry, leads to part distortion, and because of which the 3D printed parts are not acceptable because they have deviation from the desired geometry. In fact, what people have done is that they printed the identical parts, similar parts, the same CAD model on the same machine, but by keeping different settings for nozzle temperature and platform temperature. And in the process, they measure the distortion in each part. Then based upon they printed this multiple times, they generated a distortion data, and a cyber model was built to predict the deformation based upon the printing setting. So they did it for one range of printing, and basically if you have good data, you can always train a neural network, and then you can that data can be used to predict like what will be distortion if temperature, for example, changes from 200 to 205 degrees centigrade or 220 degrees centigrade or maybe 195 degrees centigrade. All these can be worked out based upon this. So based upon this printing data, the cyber model was built, and based on the results, they basically tried to control automatically the nozzle temperature with the help of CPS. So whenever they know like what is going to be the best temperature for different materials, different settings, and if the temperature is changing because of any reason, so automatically with the help of cyber physical system, the cyber physical system was developed by them. They tried to control the nozzle temperature. So the major function of the designed cyber physical system was not only to monitor the changes which are happening because of change in temperature, but to also control it. That means when they're seeing that because the temperature is changing and because of this there's a high probability of distortion coming, they will decrease the temperature so that distortion is also reduced. And this led to generation of what is called as a predictive model. So with this predictive model, the thermal stresses, which comes because of the non-uniform heating or differential temperature, and distortions can be predicted based upon the temperature at the nozzle, the bed temperature, the printing speed, and the layer thickness. So they could record the layer thickness, the speed of printing, and temperature both at the nozzle and at the bed where the material is being deposited. And with this, they tried to figure out what would be the thermal stresses and what would be the distortion. And based upon this predictive model, the model which is developed with the help of a cyber physical system, the cyber physical system can adjust the nozzle printing temperature so that the resultant thermal stresses are also reduced and they remain within the limits of the controlled parameters. So for this cyber physical system, there are 4 parts. The 4 parts are the physical system, the cyber model, the control system, and the computer. So, yesterday also we discussed there's a physical system which actually is happening. There's a 3D printing machine, the physical 3D printing machine, which is taking raw material in the form of, maybe in the form of a pellet, in the form of a wire, in the form of a powder, or in the form of a liquid. And this physical system with this design system is making parts. And it also is collecting data from the cyber model and providing feedback for control system. The cyber model is the second phase, which is like internet-based model, and it will collect data from this physical model and then can find out, like, based upon what is the temperature, what will be they will be able to predict what will the thermal stress based upon the current settings. And settings, I told you, there are 4. the nozzle temperature, bed temperature, printing speed, and the layer thickness. And based upon these current thickness and based upon the predicted thermal stresses, it can generate new set points. The set points will be like if, for example, temperature goes up from 200 degrees centigrade to 5 degrees centigrade, it will reduce back to 200 degrees centigrade. Printing speed increases by amount delta x, it will reduce by the amount delta x, so that the system works in an optimized manner, and that too automatically. There is no human intervention. It's not human being like somebody among you standing over there and trying to control system, but it is all based upon the automated setting, which is controlled by the cyber model. And then the control system is again an actual system which is connected to the physical system on the physical side and a cyber system on the virtual side, and adjust this physical system and make it run around the new set points. And there's a PC, a personal computer, which can monitor all the processes. Personal computer will be controlling the physical system. It will be also housing the cyber model, and will be also activating the control system. It is something similar to you have a sensor actuator system. So the system, physical system, will be gauged by a sensor. The data will be passed to the cyber model, like the controller basically. For example, if you talk about a human being, your brain, and then some actuation will come, which is basically come to the control system. So this is like the architecture, conceptual architecture of the cyber physical system, which was proposed by Meow et al. And if you look at carefully, at the heart of the system is basically our physical system, that is a 3D printer, which is coupled with some sensors on Arduino platform. Now, the sensors collect certain data from these 3D printer and send it to cyber system, which we call a distortion prediction model. So as discussed, they send nozzle temperature, platform temperature, bed temperature, printing speed, and layer thickness. And they also sent these 4 parameters values to remote control and monitoring system, which is a web server. You can see again nozzle temperature, platform temperature, printing speed, and layer thickness. So whenever this data is set to the distortion prediction model, the CPS, the cyber physical system, will predict will predict what is going to happen, and it will also predict the distortion set points. And these set points will go to the PID controller, which is nothing but a control system. So PID controller will activate, for example, fan speed and some temperature controllers. They will be on or off, and this data, this controller will be activated back on 3D printer. So PID controller will probably switch on some coolers, some fans, or maybe switch on or off some type of temperature measuring and controlling devices. The PID controller will also pass this control variables to the web server, remote monitoring at the web server. The web server, on the other hand, will pass this entire data to a human interface, which can be in the form of a mobile device, maybe a mobile phone or a tablet or a computer, whatever. Normally we say handheld devices because it's a user interface, and then user will give some command which will come to the remote again for the web server, and this will go to the set points. And so PID controller will have the differentiation between the predicted distortion set points and the set points. Say again, the same example of what I am giving to you. If the set point is kept at 200 degrees centigrade, and if the CPS predicts that the temperature is going to be 202 degrees centigrade, the PID controller will act and control the 3D printer. So please understand the differentiation which this system is doing and what you understand. So normally what happens is that the temperature will rise to 202 degrees centigrade and the controller will act and reduce the temperature to 200 degrees centigrade. Here we are having a CPS system which is going to predict that if these are the parameters, the temperature is going to rise to 202 degrees centigrade. And before the temperature rises, the differentiation, the error function between the set points and the predicted distortion set points will come into action. and change the parameters on the 3D printer so that the temperature never goes up to even 202 degrees centigrade. That's the beauty or the uniqueness of this particular system. And this is the actual architecture. So this was the conceptual architecture, and this is the actual architecture with the physical things. Again, at the heart of the system is our 3D printer, which is connected to some sensor node, some fans, some thermocouples, some infrared sensors, some heating cartridges, some transistors, and everything is connected with the help of a Bluetooth. And from this Bluetooth, the parameter values, the nozzle temperature, platform temperature, layer thickness, and printing speed is sent to the cyber physical system, which is distortion prediction model. And this distortion predictive model sent the predicted distortion set points. This is my PID control system. PID control system will pass this control variables to web server, that is Internet of Services, IOS. Like you know, IoT. This is also a very important factor, which we call as IOS, Internet of Services. From where, again, these 5 parameter values are passed from the 3D printer to the web server. The web server, they will pass the system status to your human interface, your mobile phone, your tab, from where you will give some user command. And based upon this command, the Internet of Services will again set the set points, and the differentiation between the predicted set points and set points will be responsible for this controller to actuate the nozzle temperature, control the nozzle temperature, the fan speed, all the on-off conditions, so that the 3D printer is controlled and temperature never rises or lowers beyond 200 degrees centigrade, because the set temperature is 200 degrees centigrade, which gives you the best possible layers on the part which is being deposited. And when the layers are best possible, then the distortion is not there, and you will have a near perfect geometry coming out of this 3D printed part. Am I clear?
Yes, sir. Yes, sir.
So this is your the actual physical setup. So this was, I said, the actual system, but again, more like a image point, like sketch point of view. And this is your actual system. So this is your 3D printer, and inside this 3D printer, you can see a thermocouple is being attached. An infrared sensor is being attached. At the top, we have coupled it with the Arduino Mega controller, and there's a thermistor over here, which sends the 4 parameters: nozzle temperature, bed temperature, printing speed, and the layer thickness, and which is being passed to the CPS system, and from CPS system to PID controller, as well as your internet service, which is your web server. This remote control and monitoring web servers, which is nothing but Internet of Services. This is the schematic of the experimental setup, which is going to control. So this is your extruder. And in this extruder, we have mounted a fan. This is the direction of moving, a thermocouple, a sensor pin, which is connected to the controller, the nozzle, the heating cartridge, this is customized sensor mount, infrared sensor, sensor pin to connect it to controller. The newly deposited this is a deposited layer. The blue color is a layer, which is by 150 mm by 20 mm. And at this point, when this image is being drawn, the height is already 5 mm. So depending upon the layer thickness, say for example, if the layer thickness is 1 micron, then it will be like something 5,000 layers have been already being deposited on this. So these blue colored ones are the physical layer, and this is the nozzle. This is the raw material which is being passed from there to be deposited from the nozzle. So this nozzle is depositing the part, and this is the actual part being manufactured. This is a circuit plot. Circuit plot will have thermocouple on this side, heating cartridge. Then we have some connector diode over here, and we have this entire is your Arduino board, and which is controlling everything. You can see you have PWM, the communication port, the analog inputs. So all are being there, and that will be responsible for giving you the input data. This is the user interface for 3D printer temperature monitor. You can see it clearly. So we can set the novel temperature, we can set the platform temperature. And this is the current status. The controller is on. The set point is 65. The temperature, platform temperature is 59.73. The novel temperature is 165. The ambient temperature is 31.6. The time is 30,778. And the part temperature is 35.89. 35.89. This is the system evaluation when ABS is 3D printed. So with CPS and without CPS, the blue colored is the with CPS and the brownish colored is without CPS. So you can see not only the distortion is less in with CPS system as compared to without CPS system, but even the fluctuations are also less. You can see the fluctuations in without CPS system are much higher as compared to with I'm sorry, with CPS system. So with CPS system, the variations is less. Here the variations also very high. Okay. Before taking the second example, any question in this?
No, sir. No questions.
Okay. If no question, let's take the second example, which is smart agriculture as a cyber physical system. And this work has been inspired by the work of Taibbi et al., who have published their paper Smart Agriculture as a Cyber Physical System, a real-world deployment in the 2020 Fourth International Conference on Intelligent Computing in Data Sciences. And this is the DOI number of this paper. And this example is basically inspired by what we discussed yesterday when we exemplified the CPS system, and I gave you one example of smart agriculture also. So here also, the cyber system, whatever designed cyber physical system is, it will continuously monitor and act upon certain physical entities. So for agriculture, it will monitor the soil, basically the humidity of the soil, the moisture content of the soil, the weather condition, like what is the temperature, what is the humidity in the atmosphere, some like particles like NOx or CX levels are not high or not. It will also monitor pumps, because if the water level in the ground is low, the water has to be supplied, and that is only possible when you actuate the pumps. Apart from there, that will have wireless sensors and actuators which connected to the control unit, which is basically the brain of this smart agriculture system, which is the main information and communication technology component in the domain of smart agriculture. And then the data which is generated here, that will be analyzed using a big data analytics tool. And the purpose is to leverage on the feedback fuzzy logic controller. They will be using a logic control, feedback logic controller, which will be, they will be using a fuzzy logic controller based upon the feedback. And the purpose is to regulate irrigation, the duration of irrigation, the different variables which are controlling the duration of irrigation, and the variables will be influenced by the temperature of the atmosphere and the soil moisture difference between the desired and the ambient value. So what are the difference between the temperatures? What are the difference between the humidity in the atmosphere? And what are the difference between the desired and actual water content in the soil? The soil moisture, what they call. So this is a basic architecture or structure of cyber physical system. So the red color is your cyber physical system, which will have a processor, your sensor and actuator. And from environment, the data is being collected with the help of sensors and passed to the processor. Processor gives some outputs, which will be passed to the actuator, and actuator will be taking action. Like for example, if the sensor record that the water level or the moisture content in the soil is low, they will be passed to, this information will be passed to the processor. The processor will analyze this data with the big data, and it will analyze that if it is like low, what is the interpretation of low? And if it is very low, then it means that the pumps has to be on for a very long period. Like for example, if the farmer is cultivating the rice crop, rice has to be immersed in water for the long duration. So he'll make sure, the cyber physical system will make sure that the pumps are kept on for the longer period of time, so that the entire field is being filled by water. And otherwise, it will be kept on for a small duration. But this decision is taken care by the cyber physical system. And this is like general architecture of cyber physical, smart agriculture cyber physical system. So this is the field which have some water sprinklers. This 1, 2, 3, 4, 5, 6, 7. They're all sprinklers, and they are also connected with a wireless sensor network, which will collect the data and pass to the internet. Internet will pass this data to control center, to the servers. We have database, and the users who are processing the data in the database on the servers, and based upon this, the control center will give some information for action to the irrigation system, and irrigation system will initiate the water supply. So as soon as this message is passed to the sprinklers will start sprinkling the water in the field. So then we have this testbed general architecture. And again, if you see carefully this system, it is very similar, but this is my, on the top is like cloud, which is big data analytics platform. We have a wireless sensor, the data which is kept by a farmer, even, weather forecast. Like for example, you notice that the water level or the moisture content in the soil is less, but then there's a probability of very heavy rain in maybe half an hour. Then why should we switch on the motors? So this weather forecast is important. The farmer data is also important because some of the crops do not require high moisture content in the soil. So what type of crop the farmer has cultivated, and what is the level of moisture required by that crop, that comes from the farmer data. Sensor data collects the data in general and from the actual or the real conditions. And for example, it will note down it will have a soil moisture content sensor, which will sense the moisture in the soil, pass that data. It also sends the humidity level in the atmosphere. It will also have various the temperature of the atmosphere, all such data. And this collection of data which comes from the sensor, from the farmer, from the weather forecasting system, that is meteorological department, we have big data. The data will become huge, what we call as big data. And this will work on the big data analytics platform. The data will be passed to the control unit, say probably Raspberry Pi controller, and which will, based upon the decision sent by the cyber physical system, intelligence system, it will actuate the actuator 1 and actuator 2. So actuator 1 will switch on the pump. Let's say pump 1 is the groundwater pump, which will lift the water from the ground and put into a basin, which is pump 2. And then from pump 2, our sprinkling system will have water and will sprinkle to the irrigation system. On the other side, how does the entire system is being powered? So we can have a solar unit, we can have a control unit, or any other mode of like battery, which is going to run these pumps. So the red color is the electricity being supplied to both the pumps, although it is showing only for pump 2, but it's basically the pump 1 will also require power. So when the actuator signal goes, basically it goes to the switching on and off of pump when they are provided with the electrical supply. When the electrical supply is there for both the cases. This is like the architecture of wireless sensor network prototype. So how different sensor network is being connected. So you can see on the left hand side, we have temperature and humidity sensor. We have a soil moisture sensor, and we have a water level sensor. And the data from these three goes to your Arduino Uno board, from where the data goes to a GSM or GPRS SIM 900 module, which will pass the data to Big Data Analytics Platform, what we call a BDAP. So from sensor to processing of big data, this is your wireless sensor network architecture. This is the way the data will be passed from one system to another. These are like the actual component deployment, and you can see them carefully. We have a power supply. We have an Arduino Uno motherboard. We have a GSM GPRS SIM 900, water level senior, soil moisture sensor, and temperature and humidity sensor. So from temperature and humidity sensor, from soil moisture sensor, the signal goes to this Arduino board, which also collect the information about the power supply and tells this system to work. If the power supply is there, it will work. If the power supply is not there, it will not work. So we also need to understand how these controllers will be powered on and off, and how can we make sure that it is always powered on when the system is working. This is like a flow chart of the entire system.
Excuse me, sir.
Sorry?
So we can see the test bed general architecture only. We are not able to see the further slides.
Sorry, what are you going to say? Able to see?
The test bed general architecture wala slide.
Your slides are not moving, Puneet.
Yes, sir. Yes.
Slides are not moving. Oh. So I'm just stopping sharing and sharing again.
Yes, sir.
So this you would see?
Yeah, this is fine.
This you would see earlier also?
Yeah, this was coming, and then next.
This was also coming?
Yeah, it is now coming. Previously, they were not coming.
Okay. So this is like the wireless sensor node prototype development. You can see like the different sensors which are actually being used: power supply unit, Arduino Uno board, GSM GPS SIM 900, water level sensor, soil moisture sensor, and temperature and humidity sensor. So from these sensors, the data is passed to the Arduino board, which will take some maybe decision based upon the instructions which are coming from the cyber physical system, the connection system, and it will switch on the power supply, and the system will be fluctuated, and then we have the water level sensors and the SIM GPS SIM, which will take care of the other corrective actions in this case. Then this is the architecture, the flow chart of the selected cyber physical system. So the first thing is that the actual soil moisture and the temperature is read from the BDAP. BDAP, I just now told you, is basically the related to how do you process the big data. So it's a big data analytics platform. Then if this actual soil moisture is less than the desired soil moisture is SMD, then it will circulate the duration of irrigation from the fuzzy logic controller unit, which is Raspberry Pi, and start irrigation. That will switch on the pump 2. Then it will wait for the duration of irrigation. Let's say you have started irrigation for 10 minutes. So this will be on for 10 minutes. And just after 10 minutes, the pump 2 will be switched off. That will stop irrigation. And then this data will be also sent to the block data analytics platform via GPRS SIM actually. On the other hand, I'll just come back to this. If the actual soil moisture is not less than the desired soil moisture, then it will be asked to read the actual water level of the basin, again from the big data analytics platform. And if the actual water level is less than 100%, then again you have to start pumping water in the basin until it reaches 100%. That means you have to switch on the pump 1. So if the water level is low in the basin, then from the groundwater, this basin is being filled by pump 1. And the irrigation system is supplied by pump 2. So if the soil moisture content is less, then pump 2 will be activated. But if the water level is low in the basin, then pump 1 will be activated, so that basin 2 is always filled, so that pump 2 can work as per desire. So we'll have start pumping water in basin until it reaches 100%. That is, we switch on the pump 1. And then after the duration till it reaches 100%, after it reaches 100%, we stop pumping. That is, pump 2 is switched off. In between, when the data is sent to big data analytics platform via GPS, the system is asked to wait for 30 minutes. And parallelly, if the actual water level is not less than 100%, again, the system will wait for 30 minutes. And even when the pump 1 is switched off, again, the system will stop waiting for 30 minutes. That it means that the resting cycle for any case, whether you have to start the pump 1 or pump 2, in this case is 30 minutes. And this you can change. This you can change based upon what type of plantation you are going to do, what type of ground conditions you are going to work on, what type of weather you are going to work on. That is based upon the climatic temperature and humidity. So all will be worked upon in such case. Then the architecture of fuzzy logic controller is this green color one is our fuzzy logic controller, which will have a fuzzification inference, a rule-based system, will have an inference engine, and a defuzzification inference. So inference engine will convert a inference of fuzzy inference into a defuzzied inference. So we'll get a real-time temperature, and we also get the soil moisture difference. That means the desired and the actual condition difference between the soil moisture. And then this fuzzy system will set the duration of integration. So based upon what is the difference in the soil moisture content, the fuzzy logic controller will take a decision that irrigation will be on for 30 minutes, 5 minutes, 1 hour, 25 minutes, or 45 minutes. And the water will be sent to the real-time soil moisture unit, which will again pass this data to the controller, where the data will, the error differentiation for SMD difference will come, and soil moisture system will done. And if there is a difference between these two, then pump 1 will be activated. If not, and if this is large, then pump 2 will be activated. So this fuzzy logic controller takes a smart decision, trying to take a decision based upon whether there is a difference in the values of the moisture content, or whether the basin is not fully filled or fully filled. So this is a test bed control board where we have a power supply, Arduino Uno board, GSM, GPRS SIM 900, and this is all actual common. So you have a controller unit, which is Raspberry Pi, actuator 1 and actuator 2. So these are like put on a test bed. In actual condition, all these will be deployed into the wide areas of the field, and there may be more than one GSM or GPRS SIMs. There will be more than one power supply units. If there can be more than one board and the controller unit also, but then they have to be networked properly, and there can be more than one actuators also. So this is like, as you can see, this is all on a test bed, but actual condition will be slightly different than what it appears to be over here in this case. And this is like you have deployed on the thing. So you see, we have a solar power system which will generating electricity. This is a basin which is filled by the groundwater, and this is a groundwater. We have a water level sensor. If the basin level water level is down, from the groundwater sensor, which can be a underground tank, which can be a boring machine, which can be a tubewell type of machine, which will the power supply will switch on, and the power will come from here to the basin. And if there is a difference between the moisture content between the ground and the actual condition, the actuator 2 will be on, and the pump of the basin will start, and that starts sprinkling the water on the ground. And this is, you can see the wireless service networks, you can see, which sends the data to the cloud basically. So based upon this, you have, you can work upon control like this. So this is the architecture which is being implemented on this particular case. Okay. Any question anybody has? So this is just a schematic representation of two different things, like how to control the distortion in 3D printed components by controlling the temperature, by controlling the influence of temperature. And the second example was of smart agriculture, where we have just discussed two parameters. In fact, primarily one, the moisture content, but there can be other systems, other parameters you can include. But please understand, if you are trying to control the larger variables, your system will become complex. But then you need not worry, because you don't have to do calculation manually. Only thing is that you have to design a robust cyber physical system which will take actions, which will take decisions and actions for you based upon the input data you have to supply. And as we say for computers or even softwares, GIGO. What is the meaning of GIGO? Anybody knows the meaning of GIGO?
Sir, what, sir?
Sorry?
What did you ask, sir? GIGO.
Can you see this term which I have written, GIGO?
Yes, yes.
This is a very standard term. When probably I was younger than even you, when the computer just started. This stands for garbage in, garbage out. So a system will behave only based upon, number one, how you design it, and how accurately and how correctly the input data you provide. So based upon these two, you will get output, which will be good or bad based upon how good or bad these terms are. Okay.
Okay.
So any question? Whether I have finished with my lecture today, I thought that we can discuss something, but you don't have any question, I can close my presentation also. Any question anybody has?
No question.
Okay. If no question, I think we can close it off. We already taken pictures, so I don't think we need to take snapshot. Or if you want, you can just quickly switch on your camera and we can take one quick photograph and then wind it up. Rahul, but Sandeep, are you there?
Yes, sir, I am present.
Switch on your camera, please.
Yes.
Okay. So ready? 1, 1, 2, 3. Okay, thank you. And let me stop this presentation. We'll meet 2 p.m. tomorrow.